This next section is about limits. In the box that you can see is a summary of the results for properties of limits. The first one there simply says that a limit of a sum of two functions is the sum of the limit of the functions. The second property says that if you have a limit of a constant times a function, the result is simply k, the constant, times the limit of the function. The third one is the limit of a product of two functions is the product of the limits. And the fourth one, the limit of a quotient of two functions is the quotient of the limits. So just by way of quick revision, have a go at these 4 exercises shown. I'll give you a few moments to do those, or you can turn the video off, work on them, and then come back. And here are the solutions. Were you able to get these? Notice in the first one, the function is a simple function, x squared minus 4. As x tends towards 2, x squared tends towards 4. So the whole function, x squared minus 4, will tend towards 0. So the limit is 0. In the second one, we have a limit of a quotient of functions. Now, the top function can be factorized into x squared minus 2 and, x minus 2 and x plus 2. Notice that x is tending to 2. It's not actually 2 at any stage. It just tends to 2. That means that x minus 2 can be cancelled out on the numerator and the denominator because x minus 2 is never actually 0. That leaves you with the limit as x tends to 2 of x plus 2. And clearly that's going to be 4. The third one I think is fairly straightforward. The fourth one, like the second one, has the form 0 over 0. So if you were just to blindly substitute x equals 2 into the numerator and the denominator, you would have 0 over 0, and that's seemingly undefined. So the strategy is to factorize the top expression and the one in the denominator. Having done that, once again, because x tends to 2, we can cancel the x minus 2 terms and end up with a quadratic expression in the numerator and a linear in the denominator. The limit there, of course, is just 3. Well, returning to the next page in our notes, we've got a bit of revision here about left and right hand limits. See how you go with this exercise. We've got a hybrid function whose graph is shown, and you'll notice that there are some jump discontinuities at x equals 2. The f of 2 itself is just minus 1, but there are some open holes on the graph sections, y equals 3 minus x and x squared minus 2. Those open holes tell us that at the point x equals 2, the function is undefined using those equations. On the other hand, the function is defined as minus 1 in the hybrid layout shown for f. Well, see how you go with completing these. I'll give you a few moments, or turn the video off and then return to it when you have the solutions. Well, here they are. Did you get them correct? The first one is just 1. What that means geometrically is if we go sliding down this function here, y equals 3 minus x, towards the point x equals 2, the y value of the function gets closer and closer to 1. So the limit is said to be 1. In the case of x tending towards 2 from above, you are actually on this function sliding down the graph, getting closer and closer to x equals 2. The function value there gets closer and closer to 3. How did we go with the next exercise? In this one, the hybrid function consists of 5 components. Notice that there is a domain change at x equals 1, at x equals 2. There isn't one at 3, but the definition at x equals 1 and x equals 2 for the function g is provided in the last 2 lines of the hybrid definition. The answers are provided. Just check to see if you get the same thing. You might like to turn the video off for a moment and then come back. On the next page, page 29, there is advice to do exercise 9i on page 333, just doing question 1. When we use CAS to do work with hybrid functions, it takes a little bit to set it up. It's not too bad. So we go to define f of x, we go to book and open up the blue icon shown there, and that gives us a place to enter a 2-part hybrid function. The domain is shown in both cases for the hybrid, and then it's just a case of entering the result and graphing. Now, in the next section, we're asked to find the function values, 2 function values and a limit using CAS. We just will need to get the f of 2, the f of minus 3, and the limit as x tends to 2 from above of f of x. So turn the video off, give that a go, see what you come up with. Well, the diagram shows for CAS what you get. You should have got 0 for the f of 2, minus 5 for the f of minus 3, and for the limit of f of x as x tends towards 2 from above, 0. Do you know where to obtain the limit expression? Continuing on, we revise in this section continuity. The function f is said to be continuous at a point C inside its domain if, as shown in the square box, the rectangular box, the limit of f of x as x tends towards C from below is the same as the limit of f of x as x tends towards C from above, and both of those quantities together are equal to the f of C. So there's another exercise here. You might like to just switch the video off for a moment or two and see how you go completing that exercise. There are 5 of them shown on this page, and you have to refer to the graph provided for each. So turn the video off and then come back when you have finished. And here are the answers. So for example, in the first one, number 1, the first bit the limit of f of x as x tends towards c from below. You are on the left-hand branch of the graph, heading towards x equals c. The y value gets closer and closer to 2, so the limit is said to be 2. In the next part, part 2, the limit of f of x as x tends towards c from above. That's from the right-hand side of c. So you're on the second branch of the graph. That's the right-hand branch. You're heading towards c along that graph. The y value is heading towards -1. The function value at c is actually -1. So the f of c is -1. Regrettably, the hole in the left-hand branch of the graph is not very clear. You may have to enlarge your picture. Let's see if we can do that to see it. Oh, there we go. I think the hole now is much more apparent. You need to refer to your notes to ensure that you see the picture accurately. So is the function continuous at x equals c? Well, clearly not, because not all three quantities are equal. They all have to be equal to each other in order to be continuous. Now, in each and every case here, none of them is continuous. So we go to the next page. And we bring an example out here. G of x is defined by the hybrid function 3x minus 1 for x less than 2, and x squared plus 1 for x greater than or equal to 2. And we have to work out whether g is continuous at 2. So I'll give you a few moments for that. Turn the video off. When you're done, turn it on again, and you'll see the answer. And there's our working. So you need to check the limit as x tends towards 2 from below as well as from above. Both values here are the same, they're both 5, but that's not sufficient to guarantee that g is continuous at x equals 2. We need to compute the g of 2. We get that from the second part of the hybrid function because the second part is inclusive of 2 in its domain. So we can use 2 to compute the g of 2 to get x squared plus 1 equal to 2 squared plus 1, which is 5. So g is continuous at 5. That means that at x equals 2, there's no break or jump in the curve. Now we come to this next section about continuity at a left endpoint. Some functions are defined on domains which include or exclude a left-hand endpoint with either an open or closed interval notation, left-hand notation being used. For example, as you can see there, if a domain is of the form c comma infinity, the square bracket around c, or c comma d with a square bracket around the c again, or c comma d, square bracket around both, then the left-hand endpoint is in the domain. In this case, we say that f is right continuous at a left-hand endpoint if the limit as you head towards c from above, that's from the right-hand side of it, turns out to be exactly the same thing as the function value f of c. Well, have a go at these on page 32. Write down whether you think, well, sorry, the answers are there already. So the answers here show the first one is not right continuous at a left-hand endpoint. There's the left-hand endpoint C in the first one. It's not right continuous because there's a hole in the graph. There's no point.